Hey guys, today we're going to be looking at intermolecular forces, polarity, and some trends of the periodic table. So first off, let's take a look at a few things that we should be talking about on the periodic table. We've got the metals, which are on the left-hand side, transition metals, and then we've got non-metals. Okay, so when we're talking about forming an ionic bond, you're going to form ionic bonds with metals and non-metals, okay? So whenever there's a metal bonding with a non-metal, you're forming an ionic bond. So metal with a non-metal. Okay, so covalent bonds. So the electrons are given away or taken away. Well, covalent bonds they're only between non-metals, so a non-metal with a non-metal, and so these are given, ionic bonds are given or taken to form an ion, and covalent bonds, the electrons are shared. Okay, so an example of a covalent bond would be like carbon dioxide. So carbon's a non-metal, oxygen's a non-metal. These electrons are shared. Okay. Now another trend that we need to look at for the periodic table so that we can understand intermolecular forces is electronegativity. Electronegativity increases from left to right in the periodic table and from bottom to top. Helium, neon, argon, krypton, xenon, radium, they're exempt. So fluorine, because it's the furthest to the right and the highest one up, is the most electronegative element on the periodic table. Furthermore, francinium is the least electronegative. Electronegativity means the ability of this element or molecule of the element to attract an electron. Okay, so let's kind of take a look at this in respect to how it relates to intermolecular forces. For example, if we have carbon, hydrogens, and we're bound to a fluorine. Fluorine is the most electronegative substance on the periodic table. It's going to pull a lot of the electrons away from the carbons and hydrogens. So imagine that the electron cloud, because fluorine is the most electronegative, it attracts a lot of the electron density. This gives it a partial negative charge, a full partial negative charge, while the carbon hydrogens have a partial positive charge, a full partial positive charge. So in the case of London dispersion forces, where it was a snapshot, ching image of the molecule, that was in random motion of the electrons. So as the electrons move around, so this is element X, if the electron moves here on this, right here on this side of the element, it's more, it has a delta negative charge wherever the electron is at, while the flip side of the molecule has the delta positive charge, okay? But that's respect to wherever the electron is flowing, okay? In the case of here, of this molecule right here, the fluorine is perpetually drawing away the electron density, so that it has always a partial negative and always a partial positive. So let's look at this and with respect to how intermolecular forces work. So it's the forces between molecules. So this is not as an extreme a case as the molecule that we just drew. These have chlorines in them, chlorides. Chlorides are extremely are electronegative. They're just not as electronegative as the fluorines. So we're going to have this partial, So we're going to have this partial negative, a partial positive, because the electron cloud is floating around here more. It's displaced the electrons that are here. The electron cloud means the region in which the electrons like to be around, to reside in. And the larger the electron cloud, so the electrons that are shared between the chlorines and the carbons and the hydrogens, we've got these partial positives, partial negatives, okay? Well, that causes an attraction between these molecules. A great example of this would be water molecule with hydrogen bonding. Although hydrogen bonding is a more complicated case than we have right here. Hydrogen bonding, the same thing happens. Oxygen is more electronegative because it's found on the more right-hand side of the periodic table than hydrogen. The periodic table is just this wonderful, wonderful resource, and it's really put out very well. It's really displayed very well. Okay, so in this case, there's what's called hydrogen bonding. Hydrogen bonding is stronger than these carbon-chlorine bondings. It's its own. It's stronger, and it has its own name. Hydrogen bonding occurs with nitrogen, oxygen, sulfur. In the periodic table, if these are bound with hydrogens, you're going to have hydrogen bonding of other molecules of the same type. In this case, we have two water molecules. The same thing would happen if we had in here an ammonia in H3. Okay, hydrogen bonding still occurs. This is still more delta negative because of it's one of these elements. It's going to bond more regularly. Okay. Now, kind of on the flip side of the coin, electronegativity also affects how well electrons are pulled away. So if electrons are shared equally amongst a molecule, so for example, they're not a bent shape, or if they are, in fact, like linear in shape, they have a nice even distribution of the electrons pulling them. For example, let's look at methane or any of the hydrocarbons. You'll show that there's a symmetry. You'll see that there's a symmetry of the hydrocarbons. There's hydrogens that are surrounding them. Each one of these hydrogens pulls the electron, or the carbons pull the electron away at an even rate. There is no delta negative because the electrons are pulled equally from the four sides. Okay, so there's no like net pull here, right? For example, the electrons are flowing this way. There's one chlorine on this side and one chlorine on this side. So there's a discrepancy in the way that the shape is of these molecules, or the position, or to say it better, the position of the chloride molecule on the carbons. See, so there's allowed this region, this delta positive. However, in the case of methane, the electrons are pulled equally. There is no distribution because it's just as probable as they go this way as they will with any other direction. So there has to be a direction when we're talking about intermolecular forces. So to touch further upon this concept of partial positive and partial negative, so like this pull of electrons to different regions, well, let's take a look at water again. Okay, water has this bent configuration. Oxygen is more electronegative than the hydrogens, giving the oxygen a partial negative, while the hydrogens have a partial positive. And we will align another negative charge, negative partial charge, and negative partial positive charges along like this. The direction of the electron density provides what's called polarity. So polarity meaning the relative orientation of the poles in the direction of an electric field. So in our case, we have this direction, and chemists actually write it out like this. They have this arrow right here, this line right here, and this shows which way the electron density lies. The electron density, think of it kind of like being a magnet. You have the negative charge here and the positive charge here. When there is no relative orientation of electrons, when they're equally distributed, even in this case right here, let's look at our friend ethane. Doesn't matter where you are, hydrogens are going to be displaced from the carbons equally. There is this carbon-carbon double bond, but we're looking at the outer molecules in respect to the polarity, because these are the atoms that are able to interact with the surrounding. The inner ones, they're kind of shielded. Okay, so there is no directional electron pole in this case. So in this case, there is no net charge. There's no partial positive, partial negative. Consequently, if you put two molecules like this nonpolar molecule together, you are going to observe that there is no attractive forces except for London dispersion forces, which is the instantaneous snapshots of electrons. In this case, though, interestingly enough, with the London dispersion forces, we have two electrons, in the way I've drawn it right here, two electrons are both going to have a partial negative charge right here because they're electrons simultaneously right here. Boiling point, well, what is boiling point anyway? The boiling point is when you give a solution enough energy that the intermolecular forces of the molecules no longer are capable of attracting the molecules. Or the temperature, when we're talking about the temperature solution, that's really the vibration of molecules, okay? So you have a lot of molecules that are moving in, quicker with respect to one another. They have higher energy. When we're talking about hydrogen bonding of water, hydrogen bonds are stronger than London dispersion forces. And if we were to have this propane molecule and then a more conventional way of drawing the propane molecule like this, so this being the carbon, this being carbon 2, and this being carbon 3, there are attractive forces, the London dispersion forces, which cause the carbons, cause the propane molecules to be attracted to one another. But since they're not hydrogen bonding, nor is there a delta negative or a delta positive charge. So to put it simply, the temperature is an energy when the energy is greater than the attractive forces boiling occurs and molecules can leave the solution.